Hey everyone, in this video we will look at another regularity condition, that is the strong convexity. An extended real valued convex function f is mu strongly convex or strongly convex with parameter mu with respect to a norm if f of theta x plus 1 minus theta y is less than equal to theta times f of x plus 1 minus theta times f of y minus mu by 2 times theta into 1 minus theta into norm of x minus y square for all x and y in the domain of f and theta between 0 and 1. This is the zeroth order characterization of strong convexity. Recall that when defining a convex function, we said that the line segment always has to be above the function curve. Here we are saying that a similar thing about a quadratic curve. As an example, consider a scalar function. We are saying that the function curves enough so that the quadratic curve is always above the function curve. Let us consider the special case when we are in an inner product space. That is, norm of x square is equal to inner product of x with itself. In such a case, a function f is mu strongly convex if and only if the function gx is equal to fx minus mu by 2 norm of x square is convex. This inequality is very interesting because it is saying that the function should be sufficiently curved so that even if you subtract a quadratic term from it, it stays convex. The proof of this statement can be done by trying to verify if g is a convex function by using the zeroth order condition given earlier. Let us take a simple example of the quadratic function half x transpose qx plus r transpose x for q positive semi-definite. Then we are saying that f is mu strongly convex if function g equal to half x transpose q minus mu times identity x plus r transpose x is convex. But we know that for a quadratic form to be convex, we need the matrix to be positive semi-definite. So we require q minus mu times identity to be positive semi-definite. Now the eigenvalues of q minus mu times identity are basically eigenvalues of q minus mu. So q minus mu times identity is convex if mu is less than equal to the minimum eigenvalue of q. In other words, the quadratic function is lambda min q strongly convex. Remember that in the previous video we showed that a quadratic function is lambda max q smooth. In fact, if q is scaled identity, then both these parameters are equal. In general, however, for any f, the smoothness parameter L is greater than equal to the strong convexity parameter mu, as is the case for quadratic functions. Another implication of this property is that if you know that a function is convex and add mu by 2 norm x square to it, then the resulting function becomes mu strongly convex. For instance, we showed in earlier videos that indicator function of a closed convex set calligraphic x is also convex. Then the function indicator function of calligraphic x plus half norm of x square is strongly convex with parameter mu is equal to 1. So far we did not say anything about the function being differentiable or smooth, and all the properties were specified without using the gradient. The first order characterization of strong convexity is possible through the use of subgradients. So let's see what subgradients are. Recall that for an extended real valued proper closed function which is convex, a subgradient gx is a vector that satisfies the first order condition f of y is greater than or equal to f of x plus inner product of gx with y minus x, where gx is the subgradient. The set of all possible subgradients at a point x is called the subdifferential set of f at x and is denoted by partial of f of x. So generally you will see that the notation gx in subdifferential of f at x, which is essentially saying that gx is one of the elements of the subdifferential set of f at x. The subdifferential set of f at x is a subset of v star, which is the dual space of v. Recall that v and v star have the same elements, but v star uses a different norm, which is the dual norm. Note that if f is differentiable, then gx is exactly the gradient of f of x. In general, for the proper closed convex functions, the subdifferential set is non-empty for all x in relative interior of domain of f. Or equivalently, a subgradient always exists for a point in the relative interior of the domain of f. Though the same cannot be said about the boundary of the domain of f. To get some intuition on the subgradient, consider the scalar function that has this corner at some x. This is the point where the scalar function is not differentiable. Then the subgradient of f is the same as the gradient of f at all the points except for this particular point. At this point, you can see that it is possible to draw a whole range of tangents that can underestimate f. The slopes of all these tangents are therefore the subgradients of f, and the set of all tangents is collected into the subdifferential set of f at x. So the subdifferential set is singleton at all the points except at this point where it is an interval. So now that we have seen the subgradient, we can write down the first order characterizations of strong convexity using the subgradient. So first we have the quadratic lower bound, which is the counterpart of the quadratic upper bound condition for smooth functions. The condition says that f of y is greater than equal to f of x plus inner product of gx comma y minus x plus mu by 2 norm of x minus y square. Note that if mu is equal to 0, this is the regular convexity condition. If mu is greater than 0, this becomes the strong convexity condition. Let us derive the quadratic lower bound condition. To do this, let us write down the zeroth order condition for z is equal to theta x plus 1 minus theta y, so as to obtain f of z less than equal to theta f of x plus 1 minus theta f of y minus mu by 2 theta times 1 minus theta times norm of x minus y square. Next, we invoke the definition of the subgradient, which says that f of z is greater than equal to f of x plus inner product of g of x comma z minus x, where g of x is a subgradient of f at x. Upon substituting z is equal to theta x plus 1 minus theta y, this gives us the bound f of z greater than equal to f of x plus 1 minus theta inner product of gx comma y minus x. So combining these two inequalities, we obtain 1 minus theta times f of x plus inner product of gx with y minus x plus mu times theta times norm of x minus y square minus f of y, whole thing less than equal to 0. Here 1 minus theta is common and can be removed if theta is assumed to be less than 1. Now we started with some arbitrary theta, so we can always assume that theta is strictly less than 1. Then the inequality can be written as f of y greater than equal to f of x plus inner product of gx with y minus x plus theta times mu by 2 norm of x minus y square, which holds for all theta except for theta equal to 1. Now we can tighten this inequality by taking the supremum over theta in the open interval 0 to 1. Essentially, we are choosing theta arbitrarily close to 1, which yields the required quadratic lower bound inequality. So this concludes the proof of the quadratic lower bound for strongly convex functions. Recall that so far we have seen two types of quadratic lower bounds. We saw one quadratic lower bound obtained for general smooth functions, and we are seeing another quadratic lower bound obtained from strong convexity. It is remarked that whenever the function is strongly convex, the quadratic lower bound implied by strong convexity is much more meaningful. Let us consider the negative entropy function x log x plus 1 minus x log 1 minus x, which is defined over the open interval 0, 1. It is possible to verify that this function is strongly convex with parameter 4. The dotted line here shows the quadratic lower bound calculated at x equal to 0.8. As you can see from this figure, the strong convexity requires the function to curve at a certain rate. And if you have a function that is flat or linear in any region, then it cannot be strongly convex but simply convex. For convex functions that are not strongly convex, mu is equal to 0, and the quadratic lower bound becomes a line, so that the inequality reduces to the first order condition for convexity. We have two more important results. First is the strong monotonicity of the subgradient operator. Let us say that gx is a subgradient of f at x and gy is a subgradient of f at y. Then we have the condition inner product of gx minus gy and x minus y is greater than equal to mu times norm of x minus y square. This condition follows by writing the quadratic lower bound for x in terms of y and then for y in terms of x, and then adding the two inequalities. The strong monotonicity property is very interesting and general. This brings us to a discussion on monotonic operators. It is possible to define an operator T from V to V star. Such an operator takes elements in V, such as x, and outputs an element in V star, such as the gradient of the function f at x. So the gradient can be thought of a type of an operator, but there are many other kinds of operators, of course, like for instance the subgradient operator. An operator is said to be monotone if it satisfies Tx minus Ty inner product with x minus y greater than equal to 0. When the function f is convex, the subgradient operator is an example of a monotone operator because gx minus gy, x minus y is greater than equal to 0, where gx and gy are subgradients of f at x and y. Likewise, an operator can be strongly monotone if it satisfies Tx minus Ty inner product with x minus y greater than equal to mu times x minus y norm square. Again, if f is strongly convex, the subgradient would again be an example of a strongly monotone operator. So there is an entire theory of monotone operators and a class of algorithms to solve variational optimization problems that are more general than convex optimization problems. Within the monotone operator theory, the subgradient of the convex function is only one example, and there are many other examples. Next, let us look at the implications of strong convexity on optimization problems. Consider an optimization problem of the form x star is equal to argmin of x in calligraphic x, f of x. For mu strongly convex function f, we have that f of x minus f of x star greater than equal to mu by 2 norm of x minus x star square. To appreciate this result, recall the quadratic lower bound, which says that f of x minus f of x star greater than equal to inner product of g of x star, x minus x star, plus mu by 2 norm of x minus x star square, where g of x star is the subgradient of f at x star. Now if gx star is equal to 0, as would be the case in an unconstrained problem, the bound we have written follows directly. In general also, it turns out that the quantity gx star inner product with x minus x star is always greater than equal to 0 for all x in calligraphic x, where gx star being the subgradient of f at x star. This is actually an optimality condition for problems of this form, and you can also derive it using KKT conditions, for instance. So given this optimality condition, you can see that we are simply dropping the non-negative term on the right hand side in order to get the required bound. An interesting implication of this bound is that for strongly convex functions, the optimality gap is lower bounded by the distance from the optimum. In other words, if the function value is close to the optimum, then you cannot actually be far from the optimum x star. So if the function is strongly convex, it rules out the possibility of having a flat region around x star, so that a point x can be far from x star while the function value is close. Further, it follows from this inequality that for such problems x star is unique because there cannot be any two x star values unless mu is equal to 0. Then we come to the useful inequality called PL inequality or the Polyak-Lojasovich inequality, which says that f of x star is greater than equal to f of x minus 1 by 2 mu times dual norm of gx square, where gx is a subgradient of f at x. A remark that this inequality is generally written for the Euclidean case, and I did not find the general statement given here or its proof for arbitrary norm spaces anywhere on the internet or in any of the references, but I was able to prove it without any problems. So to prove the PL inequality, we begin by writing the quadratic lower bound condition f of y greater than equal to f of x plus the inner product of gx comma y minus x plus mu by 2 norm of x minus y square, which holds for all y. Now in this inequality, both the left hand and the right hand sides are functions of y. So it follows that we can minimize both the sides with respect to y, and still the inequality should hold. The minimum of the left hand side with respect to y is f of x star. So we have that f of x star greater than equal to f of x plus minimum over y inner product of g of x comma y minus x plus mu by 2 norm of y minus x whole square. So let us first solve this subproblem. To solve it, let us substitute w is equal to y minus x. So we have the problem minimum over w, inner product of gx comma w plus mu by 2 norm of w square. At this stage, let us write w is equal to alpha times u, where u is a unit norm vector and alpha is a scalar greater than 0. We can always do this from the homogeneity property of the norm, but since w is an optimization variable, so alpha and u are both also optimization variables. So the problem becomes a nested problem, which is of the form minimize over alpha greater than 0, and then the inner problem is minimize over all u such that norm of u is equal to 1, alpha times inner product of gx comma u plus mu by 2 alpha square, which can be written as minimize over alpha greater than 0, alpha times minimum over unit norm vectors u, inner product of gx comma u plus mu by 2 alpha square. It can be seen that the term within the bracket is nothing but the negative of the dual norm of x. So the problem becomes minus alpha dual norm of gx plus mu by 2 alpha square. So differentiating with respect to alpha and setting the derivative of equal to 0, we get alpha equal to 1 by mu dual norm of gx. Substituting, we get minus 1 by 2 mu dual norm of gx square. So substituting this back, we get the required PL inequality. Note that while strong convexity implies the PL inequality, the converse is not true. In fact, PL inequality is more general than strong convexity. That is, there are functions that satisfy the PL inequality but not the strong convexity. This has led the researchers to analyze some algorithms by assuming only PL inequality but not assuming strong convexity. There are a few more inequalities which I will leave for the assignment. Let us consider a twice differentiable function in Rn that takes real values, and let us consider the L2 norm. For such a function, recall that the smoothness parameter L is equal to max over x of the largest eigenvalue of the Hessian. Likewise, the strong convexity parameter mu is the minimum over x of the smallest eigenvalue of the Hessian. In general, it holds that L is greater than or equal to mu. Further, the condition number of f is defined as kappa is equal to L by mu and is always greater than or equal to 1. For instance, consider the quadratic function. The condition number is given by the ratio of the largest and smallest eigenvalues of q. Suppose q is scaled identity, then the problem is well conditioned because all the dimensions are scaled equally. In the other extreme, if one of the eigenvalues of q is close to 0, then the problem is said to be ill conditioned because operations such as inverting q will have lot of errors. In fact, we will see that when the condition number is too large, the performance of most of the optimization algorithm will suffer. Let us look at an interesting property applicable for strongly convex smooth functions called the co-coercivity property. We just state it without proof and leave it for you to verify. We provide this property only for Euclidean norm in Rn. The property says that for L smooth and mu strongly convex functions, we have that gradient of f of x minus gradient of f of y, inner product with x minus y, greater than or equal to mu L by mu plus L, norm of x minus y square, plus 1 by mu plus L, norm of gradient of f of x minus gradient of f of y square. Note that we can set mu equal to 0 and get the co-coercivity property for smooth convex functions. When mu is strictly greater than 0, the general version is called the extended co-coercivity property for strongly convex functions. So that is all for the properties of strongly convex and smooth functions. Before concluding, we state the conjugate correspondence theorem without proof that links the strong convexity and smoothness of f and f star. So the conjugate correspondence theorem is as follows. If a function f is smooth with parameter 1 by mu, then its conjugate f star is strongly convex with parameter mu with respect to the dual norm. If f is proper closed mu strongly convex function, then its conjugate f star is smooth with parameter 1 by mu. So that is all for this video. We have reached the end of our discussion on the preliminaries. After this, we are now ready to analyze the various algorithms, which will start in the next video. We will begin with gradient descent for smooth functions.